Welcome to Session 10 in the video series leading up to your Technician Class License exam. In this session, I'll discuss how radio waves propagate. Depending upon the frequency, it all depends upon the sun. VHF and higher frequencies generally travel in straight lines and are not affected by much of anything. There are some exceptions, which I'll point out later in this presentation. HF frequencies, however, are dramatically affected by the ionosphere. In 1901, Marconi succeeded in transmitting the first radio signal across the Atlantic, consisting of 3 dits, the Morse code character S. In 1902, using a larger antenna on each end and much more power, he was able to begin transmitting full messages. He was using the spark gap transmitter at a frequency of about 500 kilohertz, a frequency just below the AM broadcast band. The scientific world believed that low frequencies were the only way for long-distance radio contacts to be made. As a result, the U.S. government in 1912 allocated all frequencies above 1.5 kilohertz to amateur radio operators, thinking that these frequencies were useless. By the early 1920s, though, amateur radio operators, including the ARRL's founding president, Hiram Percy Maxim, were making regular contacts around the world with very low power using these supposedly useless frequencies. By 1923, scientists had found that the ionosphere was the explanation for these long-distance contacts. The frequencies above 1.5 kilohertz were no longer useless. It didn't take long for the government to take away almost all of those frequencies and allocated amateur radio operators to only certain frequency ranges. Skywave propagation had been discovered. That is, rather than traveling along the ground as ground waves, as scientists thought they did, skywaves bounce off the ionosphere. And if the ionosphere is sufficiently charged, these waves may bounce back up off the Earth's surface to be reflected by the ionosphere once again. The ionosphere consists of charged particles created by the solar wind and solar radiation from the sun. The ionosphere changes character between night and day. During the daytime, several different layers are present. At night, some of these layers disappear and others combine. Over the next few slides, I'll describe these layers. There aren't many possible test questions about the ionosphere, but having a basic understanding of how the ionosphere works will help with understanding radio propagation in general. During the daytime, the lowest layer of the ionosphere is the D layer. At night, the D layer dissipates and reappears the next morning. I remember the name by thinking of the daylight layer. This layer of ionized particles significantly attenuates, that is, blocks or absorbs, medium and high frequency radio waves below 10 megahertz. This is the reason that during the daytime, the only AM broadcast stations you can hear are quite local. But during the nighttime, you can hear AM radio stations all across the country and from Canada and Mexico. During the daytime, these radio waves are attenuated by the D layer, but at night, they can travel up to the E layer or to the F layer and get reflected back down to the ground hundreds or thousands of miles away. The E layer is the thickest during the day and thins out significantly at night. Radio waves below 10 megahertz that get through the D layer during the day are reflected back to Earth. During the night, the E layer accounts for most of the propagation of radio frequencies below 10 megahertz. Occasionally, clouds of E layer ionized oxygen molecules will appear. This usually happens in the spring and again around the winter solstice, and is called sporadic E. At these times, frequencies up to 50 megahertz are reflected during the day and evening. Frequencies above 10 megahertz get through the D layer, and during sporadic E, they are then reflected back by the sporadic E cloud. The F layers are the highest ionospheric layers. During the daytime, they form into two layers, the F1 and F2. At night, they combine into a single F layer. The F layer is responsible for almost all HF skywave propagation for frequencies above 10 megahertz. Sunspots dramatically affect how charged the ionosphere is. They emit considerable amounts of magnetic particles and photons, which collide with the molecules in the ionosphere, causing these molecules to become charged, either positively or negatively. At night, in the absence of these streams of charged particles and photons, the ionized molecules in the ionosphere recombine to become neutralized, and the ionized layer thins out or even disappears. Sunspots increase and decrease over an 11-year period. Right now, we're in the doldrums for sunspots between solar cycle 24 and solar cycle 25, which is just starting to show some activity. The amount of ionization in the atmosphere is measured every day in Montreal, Canada, and published as the Solar Flux Index. As I'm recording this video, the solar flux has dropped to 68, and I've never seen it below 65. There are several places on the internet publishing propagation forecasts. The one most commonly used is found at QRZ.com. Here are some of the important pieces of information on the forecast. The SFI, up here in this corner, is the Solar Flux Index. Anything above 70 is considered marginal. And during high periods of sunspot activities, that number gets up to 400. SN is the number of sunspots on the sun. And as you can see, this picture of the sun, it is literally completely spotless. The HF and VHF band conditions are also listed. Here's the HF band conditions down here, and the VHF band conditions up there. You'll notice that sporadic E is currently operating on both 6 meters and 4 meters. But we don't have an allocation of 4 meters here in the United States. All right, here's where the real test questions start. VHF and UHF frequencies are generally unaffected by the ionosphere. These waves travel in a straight line, which is a good thing since these frequencies are how the astronauts communicate with the Earth. VHF and UHF frequencies do bend slightly with the curvature of the Earth. VHF and UHF frequencies can be affected by vegetation, but generally are unaffected by fog, rain, or snow. Upper UHF frequencies and up into the microwave frequencies can definitely be affected. Tropospheric ducts happen in the summertime over the Midwest states, the East Coast, and the West Coast. They're caused by upper atmosphere temperature inversions, which trap VHF's radio signals and bend them along the duct. Eventually, the duct ends and the signals fall out towards the Earth. During such an event, communications are possible over long distances on UHF and VHF signals. Unfortunately, these ducts seldom form over the mountains. Knife-edge diffraction can cause radio waves to bend over small hills or taller buildings. The signal will be a bit choppy, but definitely will be readable. Most every night, there are meteors flying through the atmosphere and burning up. They leave an ionized trail behind them, which will reflect 6-meter frequencies quite handily. These trails last for several seconds, maybe even a half a minute before dissipating, and you can bounce a signal off of them. During periods of increased meteor activity, such as during the Leonids or Perseids, you can make a lot of simplex contacts over long distances on 6 meters. Auroras also offer reflection opportunities. When space weather forecasts aurora, even though we might not be able to see it as far south as we are, point your antenna northward and see what you can hear. Aurora bounce gives a kind of a fluttery signal. People often bounce signals off the moon, particularly using some of the very weak signal digital modes. And there'll be more on that in a later session. And off of airplanes, it's kind of fun talking to someone over in the Salt Lake area from here in Tooele on Simplex, bouncing the signal off a departing Delta flight from the Salt Lake airport. We are currently in the sporadic E season, and this phenomenon has been pretty active for the past few weeks. This works best on 10 meters, 6 meters, and 2 meters, with 6 meters by far being the most efficient area. Consult the band plan for these frequencies, and you'll find frequencies set aside for sporadic E. I've made contacts into Cuba and the Caribbean from Tooele on 6 meters using sporadic E. Finally, for this session on propagation, let me introduce you to the space weatherwoman, Dr. Tamitha Skov. She publishes a weekly propagation forecast on her YouTube channel and holds regular seminars on space weather. Check out her YouTube channel either by using the link or doing a search on YouTube for Tamitha Skov. This concludes the video session on propagation. This is a fascinating subject, and we probably don't even know a tenth of what there is still to learn on the subject. Please note any questions or concerns you may have to be discussed in the next online session, or email them to me at rolandksmith.com. We'll see you online.